Imagine standing on a world where storms rage for centuries, where cyclones larger than Earth itself spin endlessly in a dance of unfathomable power. This isn't science fiction, it's Jupiter, the solar system's most enigmatic giant. A planet so massive it could swallow every other world in our cosmic neighborhood and still have room to spare. But size isn't the only thing that makes Jupiter extraordinary. Hidden beneath those swirling clouds of ammonia and hydrogen lie secrets that defy explanation, mysteries that have left even the brightest scientists scratching their heads. What is that great red spot, really? Why does Jupiter's magnetic field crackle with such terrifying strength? And what lurks in the shadowy depths of its countless unnamed moons? Jupiter isn't just a planet, it's a cosmic guardian, a silent sentinel whose gravity shields Earth from countless asteroids and comets that might otherwise hurtle our way. Yet for all its protective might, this gas giant remains one of the most puzzling places in our solar system. From its roaring auroras, brighter and fiercer than anything on Earth, to the bizarre, metallic hydrogen ocean sloshing deep within its core, Jupiter is a world that refuses to be fully understood. Every time we think we've unraveled one of its secrets, it throws another curveball our way. Even now, as our most advanced probes orbit its turbulent skies, we're left with more questions than answers. That's exactly why we're diving into the 25 most baffling mysteries of Jupiter today. Some of these enigmas might sound like they're ripped straight from a scientist's wildest dreams, like the possibility of hidden, diamond-rich rain falling in its atmosphere, or the eerie, unexplained radio emissions that pulse from its poles like a cosmic distress signal. Others are downright unsettling, like the way Jupiter's moon Europa might hide a vast, alien ocean beneath its icy shell. And then there are the phenomena that just shouldn't exist, like the way certain layers of its atmosphere rotate at different speeds, as if the planet itself is coming apart at the seams. So buckle up, because by the time we're done, you'll never look at Jupiter the same way again. One of the most jaw-dropping sights in our solar system isn't a glittering ring or a frozen desert. It's a raging storm so vast you could drop 3 Earths inside it and still have room to spare. The Great Red Spot, Jupiter's most famous feature, isn't just a temporary tempest, it's a centuries-old atmospheric beast that defies everything we know about how storms behave. Most hurricanes on Earth fizzle out after a few weeks, their energy sapped by friction or cooler waters. But this monstrous vortex has been churning since at least the 1600s, when astronomers first glimpsed it through primitive telescopes. So what keeps this crimson whirlwind alive for so long? Unlike Earth storms, which feed off warm ocean water, Jupiter's Great Red Spot is a self-sustaining engine of chaos. Scientists believe it dredges up heat and chemicals from deep within the planet's hidden layers, creating a near-endless fuel supply. And because Jupiter lacks a solid surface, no mountains or landmasses to disrupt the flow, the storm just keeps spinning, trapped between jet streams that act like invisible walls. But here's where it gets even stranger. Despite its legendary stamina, the Great Red Spot is shrinking. Early observations from the 1800s describe a storm twice as wide as it is today, and recent measurements from spacecraft like Juno show it's getting taller even as it narrows, like a giant stretching upward while being squeezed at the sides. Theories about its iconic red color are just as wild. Some suggest complex chemical reactions where sunlight breaks apart molecules like ammonia and hydrogen sulfide, creating compounds that glow like rust. Others speculate that the storm might be pulling up mysterious substances from deep below, materials we've never even seen before. And then there's the eerie possibility that the spot isn't just a storm. It might be something closer to a living system, a swirling mass of fluid dynamics that behaves almost like a cosmic organism, constantly adapting to survive. Even now, as we watch the spot's slow transformation, no one can say for certain how much longer it will last. Will it vanish within our lifetimes, fading into Jupiter's striped bands like a forgotten legend? Or could it stabilize, finding some new balance in the planet's turbulent atmosphere? Every clue we uncover only deepens the mystery, proving that even Jupiter's most familiar landmark is anything but ordinary. Deep beneath Jupiter's swirling clouds, where pressures crush matter into exotic forms, lies one of the planet's most baffling secrets, its core, or rather, the startling lack of one as we expected. For decades, scientists assumed gas giants like Jupiter harbored dense, compact cores of rock and metal, remnants of their early formation when dust and debris clumped together under gravity. But when NASA's Juno spacecraft peered into Jupiter's heart using gravity measurements, it revealed something that turned planetary science upside down. Instead of a solid, well-defined core, Jupiter's center appears diluted, a murky blend of heavy elements mixed with hydrogen, stretching across nearly half the planet's radius like some cosmic smoothie. This fuzzy core makes no sense under traditional planet formation theories. If Jupiter grew by accumulating solid material first, then sucking in gas later, its core should be distinct and intact. One radical explanation suggests a cataclysmic event billions of years ago. Perhaps a collision with a massive protoplanet shattered Jupiter's original core, scattering heavy elements into the surrounding layers. Others propose the core never fully formed, with heavy elements instead suspended like sediment in Jupiter's primordial soup of gas. The implications are staggering. If Jupiter doesn't play by the rules, could other gas giants defy expectations too? Saturn's core, for instance, is slightly better defined but still fluffier than predicted, hinting that gas giants might exist on a spectrum of core diffuseness. Yet Jupiter's extreme blurriness stands alone, raising questions about whether it's an outlier or a missing link in our understanding of planetary evolution. Even more puzzling is how this diffuse core affects Jupiter's magnetic field, the strongest in the solar system. Without a compact metallic anchor, what generates such intense magnetism? Some scientists speculate that under Jupiter's crushing pressures, hydrogen itself morphs into a bizarre, electrically conductive fluid, creating a dynamo effect far stranger than anything on Earth. Every new Juno data dump adds twists to the mystery. Recent findings suggest heavy elements might be unevenly distributed, clumping in some regions while absent in others, as if Jupiter's interior is a poorly mixed cocktail. Could this explain asymmetries in its gravity field or the erratic behavior of its storms? The answers might rewrite textbooks, proving that even a planet's deepest secrets can't stay hidden forever, especially when that planet is Jupiter, the solar system's ultimate enigma. While Earth's northern lights paint delicate ribbons of green and pink across the sky, Jupiter's auroras are something else entirely, a roaring, radioactive light show that could outshine our entire planet. These aren't just pretty cosmic decorations, they're violent, high-energy eruptions, some generating ultraviolet flares so intense they'd be lethal to any human observer. And here's the kicker: unlike Earth's auroras, which rely on solar wind particles colliding with our atmosphere, Jupiter's lights blaze with a ferocity that can't be explained by the sun alone. NASA's Juno spacecraft discovered the truth: Jupiter's auroras run on their own terrifying power grid. While solar wind does play a role, the real energy comes from deep within the planet itself. Charged particles get catapulted along Jupiter's magnetic field lines, accelerating to near-light speeds before smashing into the upper atmosphere. But the real mystery lies in the staggering voltages at play. Juno measured electric currents surging between Jupiter's poles and its magnetosphere at over 4 million volts, 10 times stronger than the most powerful auroral currents on Earth. Where does all this energy originate? One leading theory points to Jupiter's volcanic moon Io, which spews sulfur dioxide into space, creating a donut-shaped plasma cloud around the planet. As Jupiter's magnetic field sweeps through this cloud, it generates colossal electrical discharges, but even this doesn't fully account for the aurora's insane brightness. Some scientists suspect another, far stranger force at work: Jupiter's own rotation. Spinning once every 10 hours, the planet's metallic hydrogen core might act like a cosmic generator, converting rotational energy into electromagnetic fury. Then there's the bizarre structure of the auroras themselves. Unlike Earth's relatively smooth curtains of light, Jupiter's appear as chaotic, flickering ovals with strange dots and trails that pulse independently. Juno even spotted tiny, secondary auroras dancing near the equator, something no model predicted. These anomalies suggest hidden electrical pathways or even undiscovered particle acceleration zones deep within Jupiter's magnetosphere. Every new observation peels back another layer, revealing just how little we truly understand about the forces shaping this gas giant's hypnotic, deadly glow. Jupiter's magnetic field isn't just powerful, it's lopsided, like a cosmic bar magnet someone forgot to balance. While Earth's magnetic poles are relatively symmetrical, Jupiter's northern and southern magnetic hemispheres couldn't be more different. Data from NASA's Juno mission revealed a startling imbalance. The field in the north is patchy and scattered, while the south boasts a concentrated, almost blistering intensity. Picture trying to use a compass where one pole pulls twice as hard as the other. That's the kind of magnetic chaos Jupiter throws at us. The weirdness doesn't stop there. Unlike Earth, where the magnetic field emerges predictably near the poles, Jupiter's southern magnetic flux erupts from a single, bizarrely localized region the team dubbed the Great Blue Spot, an invisible, swirling concentration of magnetic energy with no real equivalent in nature. And it's drifting. This hotspot shifts position over time, creeping eastward like a slow-motion storm, dragging part of Jupiter's magnetic field with it. Scientists initially assumed this asymmetry might stem from external factors like solar wind pressure, but the truth lies much deeper, buried in the planet's alien interior. The leading suspect, Jupiter's ocean of metallic hydrogen. Under pressures exceeding 2 million times Earth's atmosphere, hydrogen, normally a gas, transforms into a shimmering, conductive fluid capable of generating magnetic fields. But this sea isn't uniform. Some regions might be more turbulent, others denser, creating pockets where magnetic dynamos fire more intensely. Researchers now suspect the southern hemisphere's metallic hydrogen layer could be deeper or more electrically charged, amplifying the field there while leaving the north comparatively feeble. Then there's the wild card, Jupiter's core, or what's left of it. The planet's diluted, fuzzy core might contribute to the lopsided magnetism, with heavy elements unevenly distributed like lumps in a cosmic batter. If metallic hydrogen swirls around these irregular clumps, it could generate chaotic, localized magnetic surges. Add Jupiter's breakneck rotation, spinning so fast it flattens the planet at the poles, and you've got a recipe for magnetic mayhem. The implications are staggering. If Jupiter's field is this unpredictable, what does that mean for other gas giants? Could similar asymmetries explain strange auroras or radio emissions from distant exoplanets? And how does this uneven magnetism affect Jupiter's moons, bathed in a lopsided torrent of radiation? Every answer from Juno feels like peeling back a layer of Jupiter's infinite strangeness, and we're just getting started. Most moons in our solar system spin like predictable tops, rotating with steady, clockwork precision. But Hyperion, Jupiter's potato-shaped oddball, dances to its own deranged rhythm. This irregular moon doesn't just rotate, it tumbles through space in a violent, unpredictable stagger, flipping and wobbling so erratically that astronomers struggle to calculate its position more than a few days in advance. Hyperion's rotation isn't merely chaotic, it's mathematically impossible. Most moons become tidally locked over time, with one face permanently turned toward their planet, like Earth's moon. But Hyperion resists this cosmic order. Its oblong shape, pockmarked with deep, spongy craters, interacts bizarrely with the gravitational pulls of Jupiter and neighboring moons like Titan, creating a feedback loop of instability. Imagine kicking a deflated soccer ball down a hill. It might bounce, roll sideways, or even flip midair without warning. That's Hyperion's daily reality, except the hill is the crushing gravity well of the solar system's largest planet. The deeper mystery lies in what this chaos reveals. Hyperion's spongy surface, so porous that impacts compress it like a cosmic stress ball, hints at a violent past. Some scientists speculate it's a survivor of a catastrophic collision, a fragment of a larger moon shattered eons ago. Others propose it never fully formed, remaining a half-baked clutter of ice and rock held together by feeble gravity. Either way, its chaotic spin acts like a time capsule, preserving clues about the brutal conditions of the early solar system, when protoplanets and moons clashed in a celestial demolition derby. Even stranger, Hyperion's tumbling might be accelerating. Observations suggest external forces, perhaps electromagnetic interactions with Jupiter's magnetosphere, are subtly altering its spin over time. If true, this tiny moon could rewrite our understanding of how celestial bodies evolve under extreme conditions. Every erratic flip carries whispers of ancient collisions, hidden forces, and the untamed chaos that shaped our cosmic neighborhood. Hyperion doesn't just defy predictions, it dares us to rethink the rules entirely. When NASA Juno spacecraft first glimpsed Jupiter's poles, it revealed something no scientist had predicted. Not chaotic tempests, but eerily perfect geometric formations of cyclones arranged like cosmic puzzle pieces. At the North Pole, 8 storms rage in a precise octagonal pattern around a central vortex, while the South Pole hosts 5 cyclones locked in a pentagon. These aren't just random clusters, they're stable, long-lasting structures that defy all known atmospheric rules. On Earth, storms either merge or repel each other within days. Yet Jupiter's polar cyclones have maintained their sculpted formations for years, dancing in place without collapsing into one another. The secret might lie in an invisible force field of swirling winds. Juno's gravity measurements suggest these cyclones are encircled by jet streams acting like atmospheric moats, fast-moving bands of gas that prevent the storms from touching. Picture children running in opposite directions on a merry-go-round. Their motion creates an invisible barrier keeping them apart. Similarly, Jupiter's polar winds may generate enough rotational energy to trap each cyclone in its own cell. But how do these storms maintain their razor-sharp geometric precision over time? Some models suggest acoustic waves resonating through Jupiter's deep atmosphere could act like a tuning fork, organizing the chaos into orderly shapes. Even stranger is the central storm at each pole, a monstrous vortex anchoring the system. Unlike hurricanes on Earth that weaken over land, these persistent giants may draw energy from Jupiter's interior, where heat rises in plumes to fuel them indefinitely. The southern pentagon's central cyclone alone spans 4,000 miles, wider than the continental United States, yet spins in perfect sync with its 5 orbiting siblings. This harmony hints at a deeper cosmic clockwork governing the poles, where fluid dynamics operate on scales unimaginable on our planet, the biggest puzzle. These polygons shouldn't be stable. Computer simulations show that such arrangements typically dissolve within weeks unless some unseen force recalibrates them continuously. One radical theory proposes that Jupiter's magnetic field, twisted by the planet's rapid rotation, influences the storms like an invisible hand, nudging them back into formation. Another idea suggests the cyclone's own rotation generates secondary circulations, mini whirlpools around each storm's edge, that lock them in place like interlocking gears. Every new Juno flyby adds layers to the mystery. Recent infrared images revealed glowing rings of warmer gas around each cyclone, suggesting they might be transferring energy through these halos like competitors sharing heat in some celestial dance-off. Even more baffling is how these structures vary pole to pole. The North's octagon is far more symmetrical than the South's pentagon, implying Jupiter's hemispheres operate by different rulebooks. One thing's certain, these aren't mere weather patterns. They're a masterclass in fluid dynamics, written in storms large enough to swallow planets, and we're only beginning to decipher their language. Jupiter should be drenched. According to most planet formation theories, this gas giant's atmosphere ought to hold staggering amounts of water, leftovers from the icy comets and asteroids that crashed into it during the solar system's chaotic infancy. But when NASA Galileo probe plunged into Jupiter's clouds in 1995, it sent back a head-scratching revelation. The air was almost desert dry. The probe's measurements suggested water levels 100 times scarcer than expected, a finding so baffling scientists initially dismissed it as an instrument error. Yet decades later, Juno's microwave radiometer confirmed the anomaly. Jupiter's upper atmosphere is far thirstier than anyone predicted. The mystery deepens when you compare missions. Voyager's flybys in the late 1970s hinted at more water deeper down, while Galileo's descent through a rare hotspot, an unusually clear, dry region, might have skewed its readings. Juno, orbiting Jupiter since 2016, paints a patchier picture. Some equatorial zones appear parched, while polar regions show fleeting signs of moisture. This inconsistency has researchers locked in debate. One faction argues the missing water isn't missing at all, it's simply buried beneath cloud layers too dense for our probes to penetrate, pooling in unseen reservoirs where atmospheric currents shove it downward. Others propose Jupiter's water might be chemically bound, locked away in compounds like ammonia hydrates that evade detection. Then there's the wildcard theory. Jupiter's water isn't uniformly mixed. Unlike Earth, where oceans distribute moisture evenly, Jupiter's turbulent weather could be hoarding water in massive, swirling storms that act like atmospheric sponges, soaking it up before instruments can get a clear reading. Juno's discovery of mushballs, theorized slushy hailstones of ammonia and water, supports this idea. These heavy, semi-solid pellets might drag water vapor deep below the clouds, hiding it from view. The implications stretch beyond Jupiter. If gas giants can selectively conceal their water, how might this affect our search for habitable exoplanets? And what does it say about the solar system's early chemistry? Every new data point twists the puzzle, proving that even something as simple as H2O can become a cosmic enigma when Jupiter's involved. Jupiter should be freezing. At its distance from the Sun, the giant planet receives only a fraction of the sunlight that bathes Earth, barely enough to warm its cloud tops to -145 degrees Celsius. Yet when astronomers first measured Jupiter's thermal emissions, they got a shock. The planet radiates nearly twice as much heat as it absorbs from sunlight, glowing like a cosmic space heater in the frigid outer solar system. This excess heat isn't just a minor discrepancy, it's an energy surplus large enough to power Earth's civilization for billions of years, and no one can fully explain where it's coming from. The leading theory points to Jupiter's violent birth. As the planet coalesced from the primordial solar nebula 4.5 billion years ago, gravity compressed its gases, heating them to extreme temperatures. Like a baked potato slowly cooling in space, Jupiter has been radiating this leftover formation heat ever since, but calculations show this primordial warmth should have faded by now. The numbers don't add up. Jupiter's cooling rate can't account for the staggering heat still pouring from its atmosphere today. That's where things get weird. Some scientists suspect an ongoing energy source deep within Jupiter's interior, helium rain. Under the crushing pressures near Jupiter's core, hydrogen, normally a gas, transforms into a metallic liquid. When helium dissolves in this exotic fluid, it might separate out like oil in water, forming droplets that fall inward like a slow-motion metallic drizzle. As these helium droplets sink, friction heats them, generating additional warmth that gradually rises to the surface. It's a process akin to rubbing your hands together on a cosmic scale, except the hands are layers of fluid hydrogen sliding past each other at unimaginable pressures. Yet even this doesn't solve the puzzle entirely. Recent data from the Juno spacecraft revealed hotspots where temperatures spike unpredictably, suggesting localized energy releases that defy conventional models. One tantalizing possibility involves tidal forces from Jupiter's moons, particularly Io, whose gravitational tug might stretch and compress the planet's interior like a stress ball, generating heat through friction. Another radical idea proposes that Jupiter's lopsided magnetic field interacts with its metallic hydrogen ocean, creating electrical currents that dissipate as heat. The most unsettling part, these theories might all be wrong. Jupiter's heat excess varies by latitude, with the equator emitting significantly more energy than the poles, a distribution pattern no current model can replicate. Some researchers speculate that deep atmospheric waves triggered by storms or jet streams could be transporting heat upward in ways we don't yet understand. Others wonder if Jupiter's fuzzy core plays a role, with pockets of heavy elements releasing latent heat as they slowly dissolve into the surrounding hydrogen sea. Every attempt to balance Jupiter's energy budget leaves scientists staring at unaccounted for terawatts, as if the planet has a hidden furnace we can't locate. This isn't just an academic curiosity. Understanding how gas giants generate and retain heat could reshape our search for habitable exoplanets. If Jupiter defies the rules, might other worlds in distant star systems do the same? For now, this overheating giant keeps its secrets close, radiating mysteries along with the warmth that baffles us all. Lightning on Jupiter doesn't crackle, it screams. While Earth's thunderstorms flicker with visible bolts and rumble with radio waves, Jupiter's electric fury operates by a stranger, almost alien rulebook. NASA Juno spacecraft made the eerie discovery: these aren't your typical lightning strikes. They're supercharged, upside down, and eerily silent where Earth's would be loudest. Instead of illuminating the planet's stormy equator where Cassini once spotted flashes, Jupiter's lightning overwhelmingly prefers the poles, clustering in bizarre, concentrated bursts that pulse like Morse code from another world. The first clue to this puzzle lies in what's missing. On Earth, lightning generates a telltale crackle of radio static, a signature so reliable we use it to track storms globally. But Jupiter's lightning, nearly radio silent in the frequencies where Earth's lightning shouts the loudest. Instead, it broadcasts in a whisper at megahertz frequencies, a spectral fingerprint suggesting something fundamentally different is happening inside those Jovian thunderheads. The culprit might be ammonia, Jupiter's atmospheric wildcard. Unlike Earth's water-rich clouds, Jupiter's storms swirl with ammonia acting as an antifreeze, lowering the freezing point of water and creating a slushy mix where charge separation occurs differently. But the real shocker is the polarity. Earth's lightning typically starts with negatively charged particles near cloud bases, leaping toward positive regions below. Jupiter flips the script. Juno's data reveals most Jovian bolts are inverted, with positive charges triggering the discharge, a phenomenon so rare on Earth it's usually only seen in violent volcanic eruptions. This could mean Jupiter's storms generate electricity through some exotic process we've never witnessed, perhaps involving ammonia-water mixtures conducting current in ways pure water vapor cannot. Then there's the polar obsession. While Earth's lightning thrives in warm, tropical latitudes, Jupiter's huddles near the poles like a hermit. One theory blames Jupiter's titanic heat engine. Sunlight warms the equator, creating stable layers that suppress storm development, while the poles receiving less solar energy rely on turbulent upwellings of heat from Jupiter's interior, creating ideal conditions for electrified chaos. Or perhaps Jupiter's lopsided magnetic field funnels charged particles poleward, supercharging storms there like a cosmic particle accelerator, the most unsettling possibility. This isn't lightning as we know it at all. Some researchers speculate these flashes could be shallow lightning, igniting in ammonia-rich clouds barely 30 miles deep, far higher than Earth's storms where exotic ice crystals made of ammonium hydrosulfide clatter together like electrified hail. Others wonder if Jupiter's mushballs, slushy ammonia water hailstones, are the key, creating charge imbalances as they plummet through atmospheric layers. Every flash Juno detects rewrites the rules. These aren't just bigger versions of Earth's storms, they're windows into an entirely different kind of atmospheric physics, where familiar forces conspire to create something utterly alien. And with each polar pass, the spacecraft captures another piece of the puzzle, a universe where electricity dances to a rhythm we're only beginning to hear. Jupiter's rings don't blaze with icy grandeur like Saturn's. They're ghostly, almost spectral, a whisper of dust and debris so faint they weren't even discovered until Voyager 1 flyby in 1979. Unlike Saturn's dazzling bands carved by frozen chunks the size of houses, Jupiter's rings are made of fine, dark particles no larger than smoke grains, scattering sunlight so weakly they're practically invisible from Earth. But their subtlety hides a violent origin story, one that might rewrite how we understand ring systems across the cosmos. The leading theory points to Jupiter's moons as accidental sculptors. Micrometeorites constantly bombard satellites like Metis and Adrastea, kicking up plumes of dust that drift into orbit around the planet. Over eons, these particles accumulate, forming the tenuous rings we see today. But here's the twist: Jupiter's gravity should have devoured this debris long ago. The rings exist in a cosmic balancing act. Just enough material gets replenished from impacts to offset what falls into the planet's maw. It's like a sandcastle on the shore, constantly rebuilt as waves erode it. Yet some scientists argue the rings could be far older, relics of Jupiter's chaotic infancy. During the planet's formation, collisions between asteroids and protoplanets would have generated vast debris fields. Most of this material spiraled into Jupiter or coalesced into moons, but a fraction might have settled into stable orbits, surviving billions of years as a faint echo of that primordial chaos. This would make Jupiter's rings not just debris trails, but fossilized snapshots of the solar system's birth. The mystery deepens when you compare them to Saturn's rings. Saturn's system is 98% water ice, reflecting sunlight brilliantly. Jupiter's rings, by contrast, are dominated by rocky, carbon-rich particles, dark as charcoal. One explanation suggests radiation plays a role. Jupiter's intense magnetic field bombards ring particles with charged particles, slowly darkening them like cosmic sunburn. Another theory proposes the material never contained much ice to begin with, originating from moons like Thebe and Amalthea, whose surfaces are rich in silicates and organic compounds. Then there's the anomaly, the halo ring, a weird toroidal cloud of dust hugging Jupiter's inner ring. This region defies orbital mechanics, with particles tilting wildly above and below the ring plane like bees around a hive. Some researchers believe electromagnetic forces are at work here. Jupiter's magnetosphere could be levitating charged dust grains, creating this ethereal structure. If true, it's a phenomenon unseen anywhere else in the solar system. Every spacecraft visit adds layers to the puzzle. Galileo spotted clumps and knots in the rings, hints of unseen moonlets stirring the debris. Juno's recent images revealed strange, transient spokes, radial streaks of dust that appear and vanish like cosmic shadows. Are these signs of fresh impacts or something stranger, like electrostatic forces rearranging particles? The answers might redefine how ring systems evolve, proving even the faintest features can hold the darkest secrets. Beneath Europa's frozen, cracked surface lies one of the solar system's most tantalizing secrets, a vast global ocean holding more liquid water than all of Earth's seas combined. This isn't some stagnant, icy tomb. Jupiter's fourth largest moon hides a dynamic, salty ocean, warmed not by sunlight but by the relentless gravitational kneading of its host planet. Every time Europa swings close to Jupiter in its elliptical orbit, the gas giant's immense pull stretches and compresses the moon's interior like cosmic taffy, generating enough heat to keep its subsurface waters liquid against the bitter cold of space. And where there's liquid water, energy, and organic chemistry, there's the spine-tingling possibility of life. The clues started mounting when the Galileo spacecraft spotted Europa's fractured, jigsaw-like crust in the 1990s. Unlike Earth's rigid tectonic plates, Europa's surface is a chaotic mosaic of ice rafts, ridges, and reddish streaks, signs of a brittle shell floating atop a sloshing interior. But the real smoking gun came in 2012 when the Hubble Space Telescope caught something extraordinary. Towering plumes of water vapor erupting from Europa's south pole, shooting over 100 miles into space. These geysers weren't just proof of a hidden ocean, they were a direct sample, spraying Europa's secrets into the void for any passing probe to analyze. What makes Europa's ocean so special isn't just its existence, it's the chemistry happening within it. Spectroscopic studies reveal Europa's surface is laced with magnesium sulfate salts, likely leaching up from the ocean below. But the bigger shock came when Hubble detected sodium chloride, plain old table salt, mixed into the icy crust. On Earth, saltwater oceans teem with life, their mineral-rich depths acting as cosmic incubators. Even more compelling are the dark, rusty stains marbling Europa's ice. These could be organic compounds, possibly even the building blocks of life, cooked up in hydrothermal vents on the ocean floor where Europa's rocky core meets its watery abyss. The parallels to Earth's extreme ecosystems are impossible to ignore. In our planet's deepest trenches, entire ecosystems thrive around volcanic vents, powered not by sunlight but by chemosynthesis, a process where microbes convert minerals into energy. Europa's ocean floor might host similar vents, spewing heat and nutrients into the water. Some models suggest its ocean could be oxygen-rich, thanks to charged particles from Jupiter's radiation belt splitting surface ice into hydrogen and oxygen, which then percolate downward through cracks. If true, Europa's waters might not only harbor microbes but complex multicellular organisms adapted to the eternal dark. NASA's upcoming Europa Clipper mission, launching in 2024, aims to settle these questions. Armed with ice-penetrating radar and mass spectrometers, it'll map the ocean's depth, salinity, and even potential hotspots of geologic activity. More daring still is the concept of a lander that could analyze plume deposits or even drill through the ice, a technological hurdle akin to punching through a frozen over Antarctica. The stakes couldn't be higher. If life exists in Europa's shadowy depths, it would prove life isn't a fluke of Earth but a cosmic inevitability, waiting wherever conditions allow. Until then, Europa's ocean remains a siren call, its icy shell a locked door hiding answers to one of humanity's oldest questions. Are we alone? Every plume, every fissure, every salt-stained crack whispers that beneath the ice something extraordinary may stir. If Jupiter's moon Europa is a frozen world hiding secrets beneath its ice, then Io is its polar opposite, a cosmic pressure cooker where the very ground itself bleeds fire. This tiny moon, barely larger than Earth's own, is the most volcanically active place in the solar system, with eruptions so violent they dwarf anything our planet has ever seen. While Earth's volcanoes smolder intermittently, Io's surface is a relentless inferno, where lava lakes bubble like cauldrons and plumes of sulfur spray hundreds of miles into space. And the architect of this chaos, Jupiter's crushing gravity, the mechanics of Io's torment are both beautiful and terrifying. Locked in a gravitational tug of war with Jupiter and its neighboring moons Europa and Ganymede, Io gets stretched and squeezed like cosmic taffy. As it orbits, Jupiter's immense pull deforms the Moon's interior, generating friction so intense it melts rock from the inside out. This process, called tidal heating, turns Io into a planetary pressure cooker, where the energy equivalent of thousands of nuclear bombs releases continuously through its thin crust. But here's the twist: not all of Io's lava behaves the same. Some flows clock in at relatively cool 700 degrees Celsius, similar to Earth's basalt. Others, like those in Loki Patera, a lava lake the size of Lake Ontario, rage at over 1600 degrees, hot enough to melt steel. What could explain such extreme temperatures? On Earth, lava composition dictates heat. Iron-rich basalt flows cooler than silica-packed magma. But Io's superheated eruptions suggest something stranger, a mantle so thoroughly churned by tidal forces that it's partially molten, with pockets of ultra-dense material rising like bubbles in a boiling pot. Some researchers speculate Io's interior might even harbor magma oceans, vast subterranean seas of liquid rock kept in perpetual motion by Jupiter's gravitational kneading. When these superheated reserves burst through the surface, they don't just erupt, they explode, launching fountains of molten sulfur and silicate hundreds of meters high. The strangest part: Io's volcanoes don't always stay put. Unlike Earth's relatively stationary hotspots, Io's plumes migrate across the surface over decades, as if the Moon itself is shuffling its deck of fire. This could mean its crust is constantly recycling, with fresh lava burying old eruptions at a rate of several centimeters per year, fast enough to resurface the entire Moon every few millennia. Then there's the atmospheric oddity. Despite being bathed in Jupiter's radiation belt, Io somehow clings to a thin but persistent sulfur dioxide atmosphere, fed by its endless volcanic belches. Yet this sky isn't uniform. It collapses each night when the Moon slips into Jupiter's shadow, freezing onto the surface like frost, only to be reignited by the next day's eruptions. It's a world caught between destruction and rebirth, where the very air is borrowed fire. Every spacecraft flyby adds new layers to Io's enigma. The upcoming Juno extended mission might capture never-before-seen eruptions, while future probes could one day map the Moon's shifting lava flows in real time. But for now, Io remains a stark reminder of gravity's power, a place where planetary forces don't just shape landscapes but set them ablaze. Among Jupiter's many moons, Ganymede stands apart, not just as the solar system's largest satellite, but as the only moon with its own magnetic field. This isn't some faint, flickering force. Ganymede generates a protective bubble strong enough to carve out a miniature magnetosphere within Jupiter's crushing electromagnetic embrace. Picture a pebble creating its own tiny ripple in a raging river. That's the kind of defiance Ganymede's magnetism exhibits against its colossal parent planet. What makes this even more extraordinary is how these two magnetic fields interact. Jupiter's magnetosphere, the largest structure in our solar system, engulfs Ganymede in a torrent of charged particles. But instead of being overwhelmed, Ganymede's field resists, pushing back with enough force to create a teardrop-shaped cavity in Jupiter's plasma stream. Inside this pocket, the Moon's magnetism channels particles along its own field lines, sparking auroras at its poles. But with a surreal twist: unlike Earth's auroras, which form oval rings, Ganymede's lights appear as twin spotlights fixed in place like cosmic lighthouses. The real magic happens when these two magnetic systems collide. Data from the Galileo spacecraft revealed something bizarre. Ganymede's auroras aren't just independent, they're nested inside Jupiter's own polar lights, creating auroras within auroras. It's as if the Moon is painting its own luminous signature over Jupiter's already glowing canvas. This celestial tug of war also generates magnetic reconnection events, explosive rearrangements of field lines that launch jets of electrified plasma at nearly 1,000,000 miles per hour. Ganymede's magnetic mystery deepens when you ask how a moon sustains such a field. Earth's magnetism comes from its churning metallic core, but Ganymede. Its core should have cooled eons ago. The leading theory points to an underground ocean of salty liquid water, sloshing beneath an ice shell dozens of miles thick. As this brine moves through Ganymede's rocky mantle, it might generate electric currents through dynamo action, a process usually reserved for full-fledged planets. Then there's the puzzle of timing. Observations suggest Ganymede's auroras flicker in ways that don't perfectly sync with Jupiter's rotation, hinting at hidden complexities in their magnetic dance. Some researchers speculate tidal forces from Jupiter might be flexing Ganymede's interior, subtly altering its magnetic output. Others wonder if the Moon's icy crust plays a role, with electrically conductive layers amplifying or distorting the field. Every new observation peels back another layer. The JUICE mission, set to arrive in 2034, aims to map Ganymede's magnetic quirks in unprecedented detail. What it finds could rewrite our understanding of how moons generate magnetism, and whether distant ocean worlds might hide similar surprises. For now, Ganymede remains a cosmic rebel, its shimmering auroras a beacon of magnetic defiance in Jupiter's shadow. Callisto looks like a relic frozen in time, a battered, pockmarked world where every crater tells a story of violence from the solar system's earliest days. Unlike its sibling Europa with its cracked, youthful ice or Eo's fire-breathing volcanoes, Callisto's surface is a museum of cosmic impacts, virtually unchanged for billions of years. Some craters here are so ancient they've accumulated smaller craters inside them, like layers in a geological wedding cake. Yet beneath this stillness lies a puzzle. How can a moon with the same basic ingredients as Europa water ice, rock, and likely an underground ocean show almost no signs of internal activity? The key might lie in what's not happening inside Callisto. While Europa gets kneaded by Jupiter's gravity, flexing its ice shell and churning its hidden sea, Callisto orbits just far enough to avoid such extreme tidal heating. Its distance from Jupiter means the gas giant's gravitational pulls are gentle, like a breeze rather than a hurricane. Without that constant internal friction, Callisto's core cooled long ago, leaving it geologically dormant. But here's where things get strange. Data from the Galileo spacecraft revealed subtle magnetic fluctuations around Callisto, hints that something conductive, possibly a salty ocean, might still lurk beneath its icy crust. If true, this ocean exists in a state of eerie equilibrium. Unlike Europa's turbulent waters, Callisto's hidden sea would be still, insulated by an ice shell up to 200 kilometers thick. No volcanic vents, no shifting ice rafts, just a cold, dark abyss, possibly older than life on Earth. Yet even in this frozen quiet, surprises could await. Some models suggest radioactive decay in Callisto's rocky core might provide just enough warmth to keep a thin layer of liquid water trapped between layers of ice. Others propose that occasional comet impacts could have delivered organic material to this underground reservoir, creating pockets of chemistry ripe for something. The real shocker, Callisto's surface might not be as dead as it seems. Recent observations reveal faint, patchy deposits of carbon dioxide frost, concentrated in shadowy craters near the equator. These patches aren't static, they shift slightly over time, possibly migrating as temperatures change. Could this mean trace amounts of gas are seeping up from below, a whisper of activity from a world we wrote off as inert? Or are these frost patterns merely the work of sunlight sublimating ice in a slow, patient dance? Then there's Valhalla, Callisto's crown jewel of chaos. This impact basin stretches over 3,000 kilometers, its concentric rings resembling a bullseye carved by a meteorite the size of a small country. The collision that created it should have shattered Callisto to its core, yet the moon's icy crust shows no signs of the viscous relaxation seen on warmer worlds. The rings remain crisp, as if the impact happened yesterday instead of 4 billion years ago. This enduring scar suggests Callisto's ice behaves more like concrete than putty, freezing catastrophes in time like a cosmic insect trapped in amber. What does this mean for the search for life? Callisto's ocean, if it exists, would be a cold, lonely place, but not necessarily sterile. Earth's deep-sea microbes thrive in similar conditions, cut off from sunlight and surviving on chemical energy alone. And Callisto has one advantage Europa lacks. Its thick ice shield blocks Jupiter's lethal radiation, creating a safer environment for complex molecules to persist. The upcoming JUICE mission might finally crack Callisto's icy code. By measuring the Moon's gravitational and magnetic fields in unprecedented detail, it could confirm whether that hidden ocean exists and whether this ancient fossil of a moon still holds secrets worth uncovering. For now, Callisto remains a testament to time itself, a world where the past isn't just remembered, it's preserved. Jupiter doesn't just have moons, it commands an entire celestial militia, a chaotic swarm of tiny, irregular satellites that outnumber its famous Galilean siblings by nearly 80-1. Most of these cosmic stragglers are no larger than city blocks, tumbling through space in bizarre, stretched-out orbits that defy the neat, circular paths of Jupiter's larger moons. These aren't native-born members of Jupiter's family. They're likely asteroids and comets snatched from the depths of space by the planet's overwhelming gravity, relics from the solar system's violent youth that have been circling Jupiter for billions of years. What's truly baffling is how these captured moons fall into distinct orbital gangs, clustering in groups with similar tilts and eccentricities. Astronomers call these families, and each one tells a story of cosmic kidnapping on an epic scale. The largest group, the Calm Cluster, contains over 20 moons all orbiting in retrograde, moving backwards against Jupiter's rotation like rebellious cosmic teenagers. Another faction, the Ananke group, orbits at such extreme angles that their paths crisscross like a tangled ball of yarn. These patterns aren't random, they're cosmic breadcrumbs pointing to a series of ancient catastrophic collisions. Here's the chilling scenario. Around 4 billion years ago, during the solar system's chaotic, late heavy bombardment, Jupiter's gravity likely intercepted a handful of rogue planetesimals, small, primordial bodies left over from planet formation. As these captives spiraled toward Jupiter, some shattered under tidal forces, their fragments fanning out into the orbital clans we see today. The math is staggering. A single asteroid breaking apart could have seeded an entire family of moons, their shared trajectories acting like a forensic fingerprint of that primordial smash-up. But the mystery deepens when you examine their compositions. Spectroscopic studies reveal these moons aren't carbon copies. Some are dark as charcoal, rich in organic compounds, while others glow faintly red, hinting at mineral mixtures forged in different corners of the early solar system. This suggests Jupiter didn't just capture one type of asteroid, it vacuumed up a menagerie of space rocks, each carrying chemical signatures from vastly different regions of the protoplanetary disk. The most tantalizing clue lies in their orbit's slight mismatches. Even within families, some moons drift slightly faster or slower than their siblings, as if something, perhaps Jupiter's shifting gravity or nudges from the Sun, has been tweaking their paths over eons. These minute discrepancies act like a cosmic clock, allowing astronomers to estimate when each family formed. Some groups appear fresher, their orbits not yet fully randomized, suggesting Jupiter might still be adding to its collection even today. What does this celestial zoo tell us about the early solar system? These captured moons are living fossils, fragments of the building blocks that never became planets, preserved in Jupiter's gravitational amber. Their clustered orbits mirror the distribution of asteroids in the main belt, hinting that Jupiter's migration in its youth scattered the solar system's small bodies like a gravitational hurricane. Every irregular moon is a time capsule, waiting to reveal secrets about the chaos from which our cosmic neighborhood was born. Future missions like ISA's JUICE could revolutionize our understanding by visiting some of these tiny worlds. Imagine landing on a calm family moon, a craggy, tar-black remnant of the solar system's birth, where one wrong step might send you tumbling into space forever. These aren't just rocks, they're the lost children of the cosmos, and Jupiter is their reluctant guardian. Jupiter doesn't travel alone. It's flanked by two massive swarms of asteroids, each locked in a gravitational dance so precise they've been parked in the same cosmic spots for billions of years. These aren't just random space rocks, they're the Trojans, ancient celestial hitchhikers sharing Jupiter's orbit in near-perfect synchrony. One group races ahead of the planet, the other trails behind, all held in place by the delicate balance between Jupiter's gravity and the Sun's pull. But what makes these asteroids truly bizarre isn't their location. It's the fact they shouldn't all be there at all. Their compositions are wildly mismatched, a jumbled museum of the solar system's raw materials that defies any simple origin story. The leading theory suggests these Trojans are time capsules from the solar system's infancy, leftover building blocks from the chaotic era of planet formation. When Jupiter barreled through the primordial disk of gas and dust, its gravity may have corralled these asteroids into their current positions like a cosmic shepherd. But here's the problem. If they're truly primordial, why do some look like they've been baked in the inner solar system's heat, while others resemble the icy relics of the Kuiper belt? Spectroscopic studies reveal a shocking diversity. Some Trojans are rich in silicates and organic compounds, resembling main belt asteroids, while others are coated in exotic ices and dark, carbon-rich materials usually found billions of miles farther out. One radical explanation proposes a cosmic heist. As Jupiter migrated inward during the solar system's early turbulence, its shifting gravity might have hurled asteroids from wildly different regions into these orbital safe zones. Picture a snowball flung from the outer solar system landing next to a scorched rock from near Mars. That's the kind of impossible pairing Jupiter's Trojans present. Even stranger, recent observations suggest a handful of these asteroids might actually be comets in disguise, their icy interiors hidden beneath dark, sun-baked crusts. The Lucy mission, set to visit multiple Trojans in the 2020s, could finally crack this case by tasting their chemical fingerprints up close. But the plot thickens when you examine their shapes. Most Trojans aren't the rugged, cratered chunks we'd expect. Many are eerily smooth, as if sanded down by some unseen force. Some even appear to be contact binaries, two asteroids gently stuck together like cosmic snowballs. This hints at a hidden history of slow-motion collisions in the early solar system, where impacts happened just softly enough to merge objects rather than shatter them. Others speculate Jupiter's gravity might be stretching and compressing these asteroids over eons, sculpting them into shapes that defy normal asteroid behavior. The biggest enigma: Jupiter's Trojans aren't unique. Neptune and Mars have their own, but Jupiter's swarm is by far the largest and most diverse. This raises a spine-tingling possibility. These asteroids might not just be bystanders to Jupiter's history, but active participants in the solar system's evolution. Some models suggest Trojan collisions could have seeded Earth with water and organic materials, making them potential delivery trucks for the ingredients of life. Others wonder if their chaotic mix of compositions holds the key to understanding how planets shuffle material across the solar system. Every new observation peels back another layer. The upcoming James Webb Space Telescope might detect frosty surfaces on certain Trojans, while ground-based surveys continue spotting weird outliers with orbits slightly off from the main groups. Are these interlopers or clues to an even messier origin story? For now, Jupiter's Trojans remain a celestial Rosetta Stone, a coded message from the solar system's birth, written in rock, ice, and orbits frozen in time. Deciphering their secrets could rewrite everything we know about how our cosmic neighborhood took shape. While Earth's mightiest hurricanes top out around 200 miles per hour, Jupiter laughs in the face of such feeble winds. Hidden within those pastel-colored bands of ammonia clouds are jet streams racing at speeds that would shred any earthly storm to ribbons, some blasting past 1,000 miles per hour, fast enough to cross the continental United States in under 3 hours. These aren't fleeting gusts but planet-spanning rivers of gas, some stretching wider than Earth itself and plunging hundreds of miles deep into Jupiter's churning atmosphere. What feeds these relentless cosmic gales is one of the greatest atmospheric enigmas in our solar system. The first clue lies in their staggering depth. When NASA Juno spacecraft measured Jupiter's gravity field, it revealed something shocking. These jet streams aren't just skin-deep weather patterns. They extend at least 2,000 miles downward, deep enough to swallow 20 Earths stacked atop one another. That's like drilling through Earth's entire atmosphere and halfway through its rocky mantle to find hurricane-force winds still howling unabated. Such profound violence defies everything we know about planetary weather, where friction and terrain usually dampen winds long before they reach such depths. One radical theory points to Jupiter's internal furnace. Unlike Earth, where sunlight powers weather systems, Jupiter radiates its own heat from within, leftover energy from its formation and ongoing processes like helium rain. This internal warmth might ignite colossal convection currents, with hot gases rising from the depths only to cool and plunge back down in endless cycles. Picture a pot of boiling water, but one where the bubbles are continent-sized and moving at supersonic speeds. These convection cells could be transferring energy upward, jump-starting the jet streams like pistons in a cosmic engine. Then there's Jupiter's breakneck rotation, spinning once every 10 hours despite its gargantuan size. This dizzying speed whips its atmosphere into a frenzy through the Coriolis effect, the same force that shapes Earth's hurricanes but amplified to nightmarish proportions. While Earth's rotation nudges storms into gentle curves, Jupiter's spin stretches atmospheric flows into those iconic striped bands, with adjacent jets screaming past each other in opposite directions. The sheer scale of this motion creates turbulence on a level we can barely comprehend, with eddies large enough to swallow planets forming and dissolving in hours. But here's the twist. No existing model fully explains how these winds maintain such ferocity without burning themselves out. Some researchers speculate Jupiter's deep metallic hydrogen layer plays a role, its electrically conductive properties possibly interacting with the planet's monstrous magnetic field to transfer energy upward. Others propose mysterious atmospheric waves undulating through Jupiter's gas layers like pulses in a transmission line, constantly re-energizing the jets. There's even a fringe theory suggesting the winds tap into energy released as helium condenses into droplets within Jupiter's interior, a process akin to a planetary-scale steam engine. The most unsettling possibility: Jupiter's winds might be self-sustaining in ways we've yet to discover. Recent Juno data revealed bizarre temperature variations at different depths, hinting at hidden mechanisms transporting heat sideways along the jet streams themselves. This could mean the winds aren't just moving gas, they're actively redistributing the energy that keeps them alive, creating a feedback loop where the faster they blow, the more fuel they generate. It's as if Jupiter's atmosphere has cracked the code for perpetual motion, laughing in the face of entropy while we struggle to comprehend the rules of its game. Every scan from Juno's microwave radiometer peels back another layer of this atmospheric onion. The spacecraft recently spotted ghostly fingers of warmer gas reaching up from the depths along the edges of jet streams, tendrils of energy that might act like cosmic accelerators, pumping extra speed into the winds. Meanwhile, infrared images show the Great Red Spot acting as a colossal windbreak, its towering walls deflecting jet streams like a boulder in a raging river. These interactions suggest Jupiter's weather operates on multiple interconnected levels, where shallow storms and deep currents influence each other in ways we're only beginning to map. What does this mean for our understanding of planets? If winds can penetrate thousands of miles into a gas giant's interior, it challenges our very definition of an atmosphere. Jupiter blurs the line between weather and internal dynamics, suggesting that for giant planets the two might be inseparable. Future missions might deploy deep diving probes to sample these supersonic currents directly, braving pressures that would crush submarines like tin cans. Until then, those striped bands will keep their secrets, whispering of forces that dwarf our earthly notions of power and scale. High above Jupiter's swirling cloud tops, where the atmosphere thins into a ghostly haze, lurks a cosmic cold case, a shadowy patch of frigid gas that defies all logic. This so-called cold spot isn't just slightly cooler than its surroundings, it's a staggering 200 degrees Celsius colder, a blistering bite of frost in the planet's otherwise searing upper atmosphere. What makes this anomaly truly bizarre isn't just its temperature, it's the fact that it's lingered for decades, possibly a scar from one of the solar system's most violent events, the apocalyptic collision of comet Shoemaker-Levy 9 in 1994. When that fractured comet slammed into Jupiter like a cosmic shotgun blast, the impacts released energy equivalent to millions of nuclear bombs, heating the atmosphere to incandescence. Yet instead of fading like a normal wound, one of these scars never fully healed. Infrared telescopes first spotted the cold spot in the 2000s, a dark smudge in Jupiter's thermosphere, the atmospheric layer where sunlight usually cooks gases to white-hot temperatures. Normally, such a disturbance would vanish within years as winds mixed it away. But this patch refuses to blend in, stubbornly holding its shape like a phantom fingerprint pressed into Jupiter's sky. Scientists suspect the cold spot might be a kind of atmospheric memory, a fossilized ripple from the comet's violence. The leading theory suggests the impacts triggered a standing wave, a planet-sized vibration in Jupiter's upper air that traps cold gas like a cosmic eddy. Picture dropping a stone into a pond, but instead of the ripples fading, one lingers indefinitely, circling the same spot for decades. On Jupiter, where jet streams rage at supersonic speeds, such stability is almost unthinkable. Yet there it sits, a quiet anomaly in a realm of chaos, but the plot thickens when you examine the spot's chemistry. Spectroscopic readings reveal traces of exotic compounds, possibly remnants of the comet itself, still suspended in the chilled gas. Some researchers speculate the cold preserved these molecules like insects in amber, slowing their breakdown. Others propose the spot acts as a sink, its colder temperatures causing heavier particles to settle and accumulate over time. Either way, it's a chemical time capsule, offering clues about the composition of both Jupiter's upper atmosphere and the ancient comet that punched through it. The most unsettling possibility, the cold spot might not be alone. Recent surveys hint at other thermal anomalies lurking in Jupiter's thermosphere, some far from the Shoemaker-Levy 9 impact sites. Could these be scars from older, unobserved collisions, cosmic bruises that never fully healed? Or are they evidence of some unknown atmospheric process, a hidden feedback loop that chills pockets of gas for reasons we've yet to uncover? What's certain is that this icy ghost challenges our understanding of planetary atmospheres. On Earth, even the largest volcanic eruptions fade from the climate record within years. Yet Jupiter, a world without solid surfaces to disrupt airflow, can preserve atmospheric trauma for generations. The cold spot isn't just a curiosity, it's a window into how gas giants process violence on scales we're only beginning to comprehend. Every new observation peels back another layer, revealing a world where even the faintest scars might outlast civilizations. Jupiter's moons come in extremes, colossal worlds like Ganymede, larger than Mercury, and swarms of tiny irregulars no bigger than skyscrapers. But between these giants and pebbles, something's missing: mid-sized moons, the middle children of the Jovian system. This cosmic gap isn't just curiosity, it's a glaring anomaly that contradicts how moons typically form around planets. In Saturn's rings, we see moons of every size, from tiny shepherds to massive titans. Even Mars, with its meager gravity, hosts two modestly sized satellites. So why does Jupiter, the solar system's grand collector, lack moons in that crucial intermediate range? The answer might lie in Jupiter's violent youth. During the solar system's chaotic early days, the gas giant's overwhelming gravity could have acted like a cosmic wrecking ball. One theory suggests mid-sized moons did form initially, only to be shattered by catastrophic collisions. Picture this: as Jupiter's gravity stirred the orbital debris around it, proto-moons the size of small countries might have slammed together at unimaginable speeds, fracturing into the swarms of tiny irregulars we see today. These collisions wouldn't just break moons apart, they'd grind them down over eons, leaving behind only the toughest fragments. But destruction isn't the only possibility. Jupiter's gravity well is so deep it might have prevented mid-sized moons from forming in the first place. In the planet's orbital sweet spots, where moons could coalesce without interference, tidal forces from Jupiter's immense bulk could have disrupted growing moonlets before they reached mid-size. Imagine trying to build a sandcastle while waves constantly wash over it. That's the struggle moon building material faced in Jupiter's neighborhood. The few moons that did grow large, like the Galilean satellites, might have been exceptions, forming early when more material was available or in unusually stable orbits. Then there's the wild card, orbital migration. Jupiter didn't stay put during the solar system's infancy. It likely drifted inward, its shifting gravity scattering smaller bodies like a gravitational hurricane. Any mid-sized moons that somehow survived formation could have been flung into Jupiter's crushing embrace or ejected into interstellar space. The Galilean moons we see today might be the sole survivors of a much richer system, their larger sizes allowing them to weather the chaos that consumed their smaller siblings. The absence isn't just theoretical, it's written in the craters. Ganymede and Callisto's surfaces are littered with impact scars, some so large they hint at vanished moons that once shared their orbits. These ghostly collision partners could have been the missing mid-sizers, their existence cut short by gravitational turmoil. Even stranger, some of Jupiter's current tiny moons cluster in groups with similar orbits, as if they're the scattered remains of a few larger progenitors that met violent ends. What does this mean for other star systems? If gas giants routinely destroy or prevent mid-sized moons, it could affect where we search for habitable worlds. Moons like Europa, with their subsurface oceans, need stability to foster life, a rarity in Jupiter's chaotic realm. The missing mid-sized moons might be more than a curiosity. They could be silent witnesses to the brutality of planetary formation, reminding us that in the cosmos, survival often depends on being too big to fail or too small to notice. Jupiter's clouds paint a masterpiece in motion, swirling bands of cream, ochre, and deep burgundy that shift like strokes on a cosmic canvas. But these aren't just pretty pigments, they're chemical fingerprints of processes we're still struggling to decode. While the white stripes are easily explained by ammonia ice crystals reflecting sunlight, the deeper hues, those mysterious browns and reds, hide secrets that challenge our understanding of atmospheric chemistry. What transforms Jupiter's palette from a simple frosty white into this riot of color? The answer might lie in a cosmic cocktail of upwelling gases, relentless radiation, and compounds we've yet to identify. Start with the ammonia. This simple compound forms Jupiter's uppermost cloud deck, where temperatures plunge to -150 degrees Celsius, freezing the gas into glittering white crystals. But descend just 20 miles deeper, and the atmosphere grows warmer, allowing ammonia to react with hydrogen sulfide, forming ammonium hydrosulfide, a compound that might explain the tawny yellows and light browns. These mid-level clouds churn like a planetary-scale vat of chemicals, their colors intensifying as they brew deeper into Jupiter's atmospheric pressure cooker. Then there are the reds, the real enigmas. these richer tones, particularly vivid in the Great Red Spot and equatorial belts, defy straightforward explanations. One leading theory points to complex molecules called chromophores, forged when cosmic rays and solar ultraviolet light bombard Jupiter's upper atmosphere. These high-energy particles could be breaking apart methane and ammonia, allowing the fragments to recombine into longer-chain organic compounds like tholins, the same substances that tint Saturn's moon Titan orange. On Jupiter, these tholins might mix with phosphorus or sulfur dredged up from the planet's depths, creating a spectrum from rusty ochres to deep wine shades. But here's where it gets weird. The distribution of these colors doesn't match predictions. The darkest bands, like the North Equatorial Belt, should theoretically be the coolest regions where gases sink and compress. Yet infrared scans reveal these zones are actually warmer than their brighter counterparts, suggesting heat from Jupiter's interior might be cooking these compounds into darker variants. Some researchers propose that convective plumes, think of them as planetary geysers, are hauling mysterious substances upward from layers where pressures exceed 1,000 times Earth's atmosphere. At those depths, chemistry operates under rules we can scarcely replicate in labs, potentially creating exotic molecules that only reveal their true colors when they rise and cool. The wild card, Jupiter's polar regions, where Juno spacecraft images revealed a surreal lavender haze. This ethereal tint might come from a photochemical smog, where charged particles along Jupiter's magnetic field lines excite trace compounds like acetylene or benzene into glowing. It's a reminder that Jupiter's colors aren't just passive reflections, they're dynamic reactions, a real-time experiment in planetary-scale chemistry where every shade tells a story of energy, motion, and hidden layers. Perhaps the most tantalizing clue lies in the spots where Jupiter's colors change over time. The Great Red Spot, once a fiery brick red, has faded to a pale salmon hue in recent decades, a shift that might signal alterations in atmospheric composition or storm dynamics. Meanwhile, smaller ovals occasionally darken from white to red, as if some unseen catalyst has been introduced to their brew. Are these transformations driven by solar activity, internal heat fluctuations, or could they be evidence of chemicals we haven't even named yet, rising from Jupiter's abyss only to fade before we fully understand them? Unraveling this chromatic code isn't just about aesthetics, it's a key to mapping Jupiter's invisible circulation. Those browns and reds act like atmospheric dyes, tracing the planet's hidden currents like ink in water. By decoding their chemistry, we might finally understand how material cycles between Jupiter's depths and its cloud tops, connecting dots between what we see and the unfathomable processes occurring below. Every shade in Jupiter's swirling tapestry is a question waiting for an answer, a reminder that even in the realm of color, this gas giant plays by its own rules. If Jupiter's auroras are a cosmic light show, its radio emissions are the soundtrack, a haunting chorus of crackles, whistles, and pulses that could pass for an alien broadcast. These aren't random static bursts but structured, almost musical signals beaming from the planet's poles, some so loud they were detected by Earth radio telescopes as early as the 1950s. Known as decametric radio emissions, these waves aren't just noise, they're the voice of Jupiter's magnetic field screaming into the void, a phenomenon tied to its volcanic moon Io in ways that still leave scientists scratching their heads. The connection between Io and these radio storms is one of the solar system's most electrifying dances. As Io plows through Jupiter's magnetosphere at 40,000 miles per hour, it doesn't just leave a trail of sulfur, it generates an electric current strong enough to power humanity's civilization 10 times over. This current flows along Jupiter's magnetic field lines, creating a plasma tunnel between the moon and the planet's poles. When charged particles in this tunnel accelerate, they don't just spark auroras. They unleash radio waves at frequencies your car stereo could pick up if you drove close enough. The result, a symphony of shrieks and hums with patterns so rhythmic early astronomers nicknamed them Jupiter's song. But the music isn't perfectly predictable. While Io's orbit acts like a metronome, triggering bursts roughly every 42 hours, the signals themselves are riddled with quirks. Sometimes the radio storms fire milliseconds early or late, as if Jupiter's magnetic field hesitates before responding. Other times, the emissions split into dual frequencies, harmonizing like ghostly duets, and occasionally they vanish entirely for weeks, leaving telescopes scanning static. These deviations suggest hidden forces at play, perhaps turbulence in the plasma torus around Io, or fluctuations in Jupiter's own magnetic field strength. The weirdest twist, not all emissions point back to Io. A subset of radio bursts, dubbed non-Iodium, erupt without the Moon's prompting, possibly triggered by unseen instabilities in Jupiter's magnetosphere or interactions with solar wind. Some even pulse in opposite hemispheres simultaneously, like a planetary stereo system gone haywire. Then there's the L-bursts versus S-bursts dichotomy, long, wailing tones versus rapid clicks, each hinting at different particle acceleration processes we've yet to untangle. What makes these radio storms truly eerie is how they mimic Earth's lightning but scaled to planetary insanity. While our thunderstorms produce crackles in the kilohertz range, Jupiter's decametric waves roar in the tens of megahertz, their power amplified by the planet's monstrous magnetic field. Yet unlike Earth's discharges, which last milliseconds, Jupiter's can persist for hours, their waveforms twisting into intricate shapes when plotted on spectrograms. Some resemble whale songs, others like modem dial-up tones from hell. The Juno spacecraft's close passes have added new verses to this cosmic ballad. Its WAVES instrument captured ultra-high-resolution samples, revealing substructures within bursts, microsecond spikes, and dips suggesting previously undetected particle beam dynamics. Even stranger, Juno found emissions sometimes originate far from where models predicted, as if Jupiter's magnetic field has secret radio transmitters hidden in its plumbing. These radio mysteries aren't just academic, they're teaching us how colossal magnetic fields interact with moons and plasmas across the universe. Exoplanets with similar setups might broadcast their own versions of this song, offering clues to their compositions and moons. For now, Jupiter's soundtrack remains a mix of physics and poetry, a reminder that even in the silent vacuum of space, the cosmos finds ways to scream. We've always pictured Jupiter's jet streams as titanic rivers of gas, drilling thousands of miles into the planet's churning depths until Juno shattered that assumption with a single bombshell measurement. The spacecraft's gravity data revealed these supersonic wind bands aren't the planet-spanning behemoths we imagined. They're surprisingly shallow, barely scraping 300 kilometers deep before fading into oblivion. That's like claiming Earth's hurricanes stop cold at the top floor of a skyscraper, leaving the atmosphere below eerily calm. This revelation doesn't just tweak our models, it upends decades of planetary science, forcing us to rewrite the rules of gas giant weather from scratch. The implications ripple outward like shockwaves. If jet streams don't tap into Jupiter's interior heat, what fuels their relentless speed? Earth's weather draws energy from sunlight heating the surface, but Jupiter's shallow winds exist too high for internal heat to reach them directly. One radical theory suggests these bands might be self-sustaining swirls, their rotation amplified by smaller storms merging like droplets in a cosmic whirlpool. Picture spinning a cup of coffee. The liquid nearest the surface moves fastest while deeper layers barely stir. Jupiter's atmosphere could operate on a similar principle, with turbulence near the cloud tops feeding energy downward in reverse of what we assumed. Even stranger are the boundaries between jet streams. Juno's microwave scans unveiled a hidden layer of ammonia-rich air acting like atmospheric shock absorbers, regions where wind speeds plummet abruptly. These transition zones might function as planetary gears, transferring momentum between adjacent bands without allowing them to fully mix. It's as if Jupiter's striped appearance isn't just cosmetic. The planet has built-in mechanisms to keep its riotous weather strictly compartmentalized. The real puzzle lies deeper. Below the shallow jets, Juno detected slower-moving currents that mirror the surface patterns but lag behind like sluggish echoes. This suggests Jupiter's atmosphere operates on multiple disconnected tiers, a fast-moving skin over a more languid underbelly, with some unknown process preventing full vertical mixing. On Earth, cold fronts and warm fronts intertwine through the entire troposphere, but Jupiter seems to have erected invisible barriers separating its atmospheric layers like floors in an apartment building. What does this mean for other gas giants? If Jupiter's deepest winds don't connect to its interior energy, models of exoplanet atmospheres might need drastic revisions. Those distant worlds could harbor similarly stratified weather systems, their dazzling cloud tops masking a far simpler circulatory system beneath. Juno's findings serve as a humbling reminder. Even the most familiar planetary features can hide radical secrets, challenging us to look beyond assumptions. Jupiter's jet streams aren't the planetary arteries we thought. They're more like intricate surface tattoos, beautiful but skin-deep, hinting at deeper mysteries still pulsing unseen below. Among Jupiter's ever-shifting tapestry of storms, one peculiar formation stood out like a cosmic ink blot, an eerie, hook-shaped cloud so distinct it earned the nickname the Flamingo from stunned amateur astronomers. Unlike the planet's sprawling cyclones or churning belts, this structure curled inward like a celestial comma, its pale pink hue stark against the surrounding ammonia haze. First spotted in 2019 through backyard telescopes, the Flamingo defied immediate classification. Too organized to be random turbulence, yet too ephemeral to match Jupiter's enduring landmarks like the Great Red Spot. Was it a freak atmospheric eddy or evidence of a deeper, unseen process twisting the gas giant's skies into fleeting sculptures? The Flamingo's most striking feature was its uncanny stability. While most Jovian storms morph or dissipate within days, this hook persisted for weeks, drifting lazily along the southern edge of the North Temperate Belt. High-resolution images revealed finer details, tendrils of darker material spiraling into its curve, suggesting a vortex capable of dredging up deeper atmospheric layers. Yet, unlike Jupiter's classic ovals, which rotate like compact wheels, the Flamingo seemed to fold inward, its motion more akin to a ribbon caught in a gentle breeze. Planetary scientists scrambled for analogs, comparing it to everything from Earth's rare hook echoes in supercell thunderstorms to the unstable Kelvin-Helmholtz waves that ripple along cloud boundaries. One compelling theory points to wind shear, a dramatic speed difference between adjacent jet streams acting like invisible scissors to sculpt the cloud. On Earth, wind shear tears hurricanes apart, but Jupiter's supersonic flows might twist storms into unnatural shapes before they dissipate. The Flamingo could have been a transient cyclone caught in this celestial tug of war, its structure stretched and pinned into that bizarre hook by competing currents. Alternatively, it might represent a rare soliton, a self-reinforcing atmospheric wave that maintains its shape while traveling, like a ripple frozen in time. The color offered another clue. While most of Jupiter's whitish clouds are ammonia ice, the Flamingo's subtle pink tint hinted at chemicals from deeper down, possibly ammonium hydrosulfide or organic compounds glowing under ultraviolet light. This raised the tantalizing possibility that the cloud was a chimney, funneling material upward from layers where temperatures and pressures transform simple molecules into complex ones. If so, studying its composition could have provided a snapshot of Jupiter's hidden atmospheric chemistry, but the greatest enigma was its disappearance. By 2021, the Flamingo had vanished without a trace, leaving no comparable structure in Juno spacecraft images or subsequent amateur observations. This fleeting nature makes it either a once-in-a-generation fluke or a harbinger of phenomena we've yet to understand. Unlike Saturn's hexagonal storm, which pulses predictably at its pole, Jupiter seems capable of conjuring and dissolving atmospheric oddities on a whim. Future observers might spot new flamingos hiding in the planet's chaos, each one a stroke of luck, a puzzle written in vapor and wind, and a reminder that even in an age of robotic explorers, Jupiter guards its mysteries jealously. Jupiter's radiation belts should be terrifyingly consistent, a relentless storm of charged particles trapped by the planet's monstrous magnetic field, churning in predictable orbits like a well-oiled cosmic particle accelerator. But when a Juno spacecraft plunged into this radioactive gauntlet, it found something far stranger: belts that fluctuate wildly in intensity, sometimes surging to 1,000 times Earth's Van Allen belts only to abruptly wither away. These aren't just minor ripples in Jupiter's electromagnetic ocean, they're tsunami-sized swings that defy every model of planetary radiation, leaving scientists scrambling to explain what's juicing up or abruptly draining the most hostile environment in the solar system. The first clue lies in the belt's erratic geography. Near Jupiter's equator, radiation levels follow a rough rhythm, peaking where magnetic field lines squeeze particles into dense shells. But closer to the poles, the rules break down. Juno's star tracker cameras, originally designed for navigation, began picking up unexpected flashes as the spacecraft skimmed these regions. These weren't instrument glitches, but direct hits from ultra-high-energy electrons, striking with such violence they mimicked celestial landmarks in the sensors. Even more bizarre, these particle bombardments varied dramatically between orbits, as if some invisible hand were tweaking Jupiter's radioactive spigot by the week. Solar activity plays a role, but not the one you'd expect. When the Sun spews charged plasma in coronal mass ejections, Earth's radiation belts swell predictably. Jupiter's, however, react backwards. Solar storms sometimes deplete its outer belts as incoming particles disrupt the delicate balance of trapped electrons. Other times, a solar sneeze triggers chain reactions in Jupiter's magnetosphere, accelerating particles to near-light speeds through a process called ultra-relativistic electron acceleration. Imagine blowing on a dandelion only to have some seeds slow down while others rocket away like bullets. That's the level of counterintuitive chaos Juno witnessed. The real enigma lurks deeper. Jupiter's inner radiation belts home to the most lethal particles very independently of solar input, hinting at internal drivers. One leading suspect is the volcanic moon Io, whose constant eruptions feed a donut-shaped plasma torus around Jupiter. As this torus interacts with the planet's magnetic field, it may act like a cosmic generator, injecting fresh particles into the radiation belts during turbulent periods. Data from Juno's Waves instrument revealed eerie, Whistler-mode waves, electromagnetic pulses that can both energize and scatter electrons, rippling through these regions at critical moments, as if tuning the belt's intensity like a dial. Then there's the wild card, Jupiter's own atmosphere. The planet's ultraviolet auroras, far more powerful than Earth's, might be leaching energy from the radiation belts during particularly intense displays. Juno spotted bursts of decametric radio emissions coinciding with sudden belt depletions, suggesting electromagnetic waves could be kicking particles out of orbit like a planetary-scale pinball machine. Even more unsettling are the belts' holes, pockets of unexpectedly low radiation that appear and vanish without clear cause. Some researchers theorize these could be tunnels carved by rare, ultra-dense plasma clouds ejected from Jupiter's magnetotail, though no probe has yet captured one in the act. For spacecraft, these fluctuations aren't academic, they're a matter of survival. Juno's titanium vault, shielding its electronics from radiation, was designed based on pre-mission models that now look hopelessly optimistic. The spacecraft regularly ducks beneath the worst belts during its polar orbits, but even brief exposures have degraded its solar panels and instruments faster than expected. Future missions, like ESA's Jupiter Icy Moons Explorer, must account for this capriciousness or risk having their systems fried by a surprise particle storm. The deeper mystery, Jupiter's radiation belts might be teaching us that all magnetospheres, even Earth's, are far less stable than we assumed. If the solar system's largest particle accelerator can't decide how hard to rev its engines, what does that mean for exoplanets with similarly chaotic magnetic fields? Every erratic pulse from Jupiter's belts whispers that we've barely begun to understand how cosmic forces sculpt the invisible frontiers of planets. Amid Jupiter's swirling chaos, where storms rage and vanish with cosmic indifference, one formation defies the planet's reputation for turbulence: the String of Pearls. This celestial necklace, strung along a single latitude in Jupiter's southern hemisphere, isn't a fleeting arrangement of clouds but a lineup of pristine white oval storms, each nearly as wide as Earth, spaced with near mathematical precision. Unlike the planet's other tempests, which jostle and merge like drunken giants, these ovals have held their positions and shapes for decades, a serene counterpoint to the cacophony around them. How can such order exist in a realm of chaos, and what invisible hand keeps these pearls from colliding or dissipating like every other storm in Jupiter's atmosphere? The symmetry is almost unsettling. 8 nearly identical ovals, some observed since the Voyager flybys of the 1970s, dot the southern temperate belt like beads on a string, each separated by roughly the same gap. On a planet where jet streams scream past at 1,000 miles per hour and cyclones erupt without warning, this consistency borders on miraculous. Earth's weather systems can't maintain such discipline for weeks, let alone half a century. The leading theory suggests these pearls are antisolar vortices, storms that rotate opposite to Jupiter's prevailing winds, creating a self-reinforcing buffer zone around each one. Picture a line of spinning tops, each repelling its neighbors through sheer centrifugal force, locked in a delicate gravitational waltz that prevents encroachment. But the real mystery lies in their formation. Most of Jupiter's storms emerge from mergers or upheavals, but the String of Pearls appears to have crystallized from a single, gargantuan storm that fractured like a pane of glass. In the 1930s, astronomers observed a colossal white oval, dubbed the Great White Spot, stretching across the same latitude. By the time Voyager arrived 40 years later, it had shattered into the pearls we see today, as if some unseen planetary tension had snipped it into even segments. This wasn't random fragmentation, but a process eerily reminiscent of fluid dynamics experiments, where a long vortex spontaneously breaks into evenly spaced eddies under specific conditions. Jupiter, it seems, conducted the same experiment on a planetary scale. What keeps them apart? The answer might lie in the planet's hidden orchestra of atmospheric waves. Just as vibrations on a guitar string create standing waves with fixed nodes, Jupiter's jet streams could be resonating at frequencies that pin the pearls to their positions. Data from the Juno spacecraft hints at deep-rooted oscillations beneath the storms, rhythmic pulses that might act like atmospheric bumpers, preventing drift. Alternatively, the pearls could be riding a waveguide, a narrow band where wind speeds and the Coriolis affect balance perfectly, turning each storm into a self-cleaning whirlpool that sheds turbulence before it can disrupt the chain. The most haunting possibility, the String of Pearls, might be a fossil. Some models suggest these storms exist in a metastable state, their spacing and longevity the result of conditions that prevailed when they formed conditions that no longer exist elsewhere on Jupiter. Like ice cubes lingering in a warm drink, they're remnants of an older, more orderly atmospheric regime, preserved by chance in a special zone where turbulence hasn't yet erased them. If true, their eventual fate, whether they'll merge, fade, or persist for centuries, could reveal how Jupiter's weather evolves over timescales far longer than human observation. For now, they remain one of the solar system's most elegant riddles, a testament to the hidden harmonies lurking within chaos, a reminder that even giants like Jupiter obey laws we've yet to fully decipher. Every storm in that string is a clockwork jewel ticking silently against the roar of the planet's endless storm, and as long as they endure, they'll challenge our assumptions about where order ends and where chaos begins. From the boiling depths of its fuzzy core to the swirling chaos of its cloud tops, Jupiter remains the solar system's greatest enigma, a planet that constantly defies our understanding. We've peeled back layers of its mysteries, yet every answer only reveals deeper questions. Why does the great red spot rage on for centuries while shrinking before our eyes? What fuels those supersonic jet streams that carve through its atmosphere like cosmic rivers of fire? And how can a planet with no solid surface generate the most powerful magnetic field in our celestial neighborhood? Even Jupiter's seemingly orderly features, like the geometric storms at its poles or the haunting string of pearls whisper of physics we've yet to decipher. And then there are the moons, each a world of its own, each guarding secrets that could redefine life's boundaries. Europa's hidden ocean, richer in water than all of Earth's seas combined, might harbor ecosystems thriving in eternal darkness. Eo's volcanoes spew lava fountains taller than mountains, powered by Jupiter's relentless gravitational kneading. Even Callisto, that ancient fossil of a moon, hints at a buried sea where time moves slower than glaciers. Together, they form a miniature solar system of possibilities, challenging our assumptions about where life could exist and how worlds evolve. But the story isn't over. Humanity's next chapter of Jovian exploration is already being written. NASA Europa Clipper, launching soon, will skim just 25 miles above that icy moon's surface, mapping its subsurface ocean with radar and tasting its plumes for chemical fingerprints of life. ESA's JUICE mission will stalk Ganymede, probing its magnetic field and hidden seas for clues to how moons become worlds. And here on Earth, telescopes like JWST are decoding Jupiter's auroras and storms in wavelengths we've never seen before. So what's your favorite Jupiter mystery? Is it the way its lopsided magnetic field crackles with unexplained energy, the eerie radio symphonies pulsing from its poles? Or maybe the way its missing mid-size moons hint at a violent past we can barely imagine? Drop your thoughts in the comments, because every time we gaze at Jupiter, we're not just looking at a planet. We're staring into a cosmic mirror, reflecting how much we've learned and how much we have yet to discover. And that's the real magic. Solving these puzzles won't just unlock Jupiter's secrets, it could rewrite the rules of planetary science itself. From the way gas giants form to the recipes for habitable moons, every revelation ripples across the cosmos, shaping how we search for life beyond our solar system. Jupiter isn't just a world, it's a teacher, and its most extraordinary lessons may still be waiting in the darkness, ready to surprise us when we least